Hello.
Hello. How is everyone? Good. Oh, good.
The weather seems so nice. It's definitely a time to like go outside.
Yeah, it's actually very pleasant. Yeah, I just had for lunch. I went out quickly. It's not too hot, not too cold, not yet humid, so it's very good. Are you in New York?
Yep. I think quite a lot of people are also in New York, I think.
From the course or in general? Yeah. I see. Yeah, that's good. Okay, we'll wait for the typical 3 minutes. All right, let's get started for today. And I'll try to share my screen here. All right, so before we get started with material, I just want to announce the office hour. Yeah, there was the question last class about office hours, and I'm gonna do from next week the office hours on Wednesdays. Okay, let me say, yeah, office hour. That's gonna be Wednesdays 2 to 3 is what I propose. Does that work for the majority of you? Maybe you can quickly indicate with thumbs up or something like that. That is okay, and if not, yeah, let me know. Okay, seems like this is something that works for many at least. And if that doesn't work for whatever reason, I mean, you can also send me email, and we can find the alternative time. Great. So yeah, let's quickly recap what we discussed in the last class. Well, in the last class, we actually started to look into quantum information really dedicatedly, and discuss the notion of a quantum register, which is the use of not only one qubit but several qubits, and the most general expression to actually capture the content of an n-qubit system. What makes this powerful is that the information content that can be stored in it is scaling as 2 to the n. And for n of just a few hundred, you basically get an incredible amount of information that you could store in such a superposition state of n qubits. Then very important, we changed the notation to the typical quantum information way of looking at the Bloch sphere with this, with the state 0, with the state 0 on the top of the Bloch sphere and the state 1 at the bottom at the Bloch sphere. We looked at vector representation of a qubit system with a vector with 2 entries. For a 2-qubit system, logically, then it's a vector with 4 entries. For a 3-qubit system, it's a vector with 2 to the 3 entries, so it's 8 entries. But most important is the consideration of 1-qubit and 2-qubit states, because in quantum information, at least the canonical picture of quantum information, all quantum circuits are built out of gate operations that either act on a single qubit or on pairs of qubits. And we started to discussing this idea of quantum logic circuits that act on an array of qubits and then spit out a vector, or a vector that describes an n-qubit output state, and then to actually extract information out of it, a net measurement needs to happen, which then, and that's an important subtlety to always keep in mind, the output is actually n classical bits. Then we started to discuss single qubit gates and realized that operations on a single qubit can always be formulated in the shape of a 2x2 matrix that is unitary. The important thing about unitary matrices or unitary operators in general is that they keep the length of the vector constant, which is important in quantum mechanics, because the vector is always such that C0 absolute value squared plus C1 absolute value squared needs to be 1. And then we introduced 3 very important quantum gates, single qubit quantum gates, the X gate, the Z gate, and maybe the most important of all of them, the Hadamard gate, which is the gate that allows you to make out of an initial state a superposition state of state 0 and state 1. Then we looked at the interpretation of these gates on the Bloch sphere. So we looked at the Bloch vector rotations that happen as a consequence of these gates. And then we made an example in the end where we combined 2 of these gates. And today we are adding the second important concept here is the concept of 2-qubit gates. And basically, the lecture part today on my part will only be like 15 to 20 minutes. And then this today will be the first lecture where we actually enter also some experimental stuff. And for that, actually, Aiden, our TA that you already know, will take over. So it's going to be exciting to see actually some real experiment stuff going on. Okay, let's then go to the new sheet here. Okay, and continue with 2-qubit gates. And here we are actually focused on just one of them, and it's really the most important one, because turns out with the qubit gate that I will just, 2-qubit gate that I will just show you, and single qubit gates, as I showed you last class, you can construct basically any quantum logic circuit by combining them in a smart way, similar to the universality of the NAND gate in a classical computer that we briefly mentioned in the last class. And well, in the 2-qubit gate, you put in 2 qubits So the input is 2 qubits, Q1 and Q2. And the gate that we are going to discuss here is the so-called C-NOT gate. It's called C-NOT because that is the abbreviation for controlled NOT. So the action of a NOT gate here is triggered by a control qubit, and the Q1 here we call the control qubit, and Q2 is in our case here the target qubit. And then there is the output where, yeah, these 2 qubits are turned into a new qubit state, Q1 prime and Q2 prime. So that's the output. Okay, so there's also a notation for this 2 qubit gate, for the C-NOT gate, and that is this symbol. So the top one is the control qubit, and the bottom one is the target qubit. And how does the controlled NOT gate work? Well, let's assume A and B are numbers from the set 0 and 1, so basically describing the basis states of our system. Then the control qubit in this gate stays unaffected. It remains A. And the target qubit is going to turn out to be the value B plus or summation modulo 2 with A. So here this plus with a circle around it is summation modulo 2. So so you probably you've seen this before. So so you always you take the sum of the 2 numbers and then you divide by 2, and what remains is the value of this operation. So for 1 plus 1 modulo 2, what is the result? Any quick answers? Yep, 0, exactly. And likewise, 0 plus 1 modulo 2 is 1, and 1 plus 0 is also 1. So basically, the only interesting case is 1 plus 1, where the outcome is 0. So okay, so with this information, we can actually write down the truth table of this operation. So we go through all the possible cases. We have input, and then we have here the output. And on the left, we write the control qubit, and on the right, we write the target qubit, and likewise on the output, the same. And there we have the case for state 0 and state 0. And then I just, for convenience, I don't write here the brackets or the cats. I just write the numbers inside 0 and 1, 1, 0, 1, 1. Just, you know, treat this as if they were state cats, so you can write it down in your notes. And the output here is then, so the control qubit is never changed in the operation. So it stays 0, 0, 1, 1. And the target qubit doesn't change when the control qubit is 0. But it will change when the control qubit is 1. Then our state will, or our target state will feel a NOT operation. So when the control qubit is 1, a 0 turns into 1, and a 1 turns into 0. So that is the operation, and this is also possible to formulate this in matrix form. So in matrix form, this truth table gives rise to a matrix that reads 1, 0, 0, 0, 0, 1, 0, 0. So that means that the control qubit is unaffected. And then we have here 0, 0, 0, 1 and 0, 0, 1, 0. So the fact that this is deviating from a diagonal matrix here, especially here in this bottom 2 by 2 submatrix, shows that the state of the target qubit is exactly flipped. And this matrix we would apply then on a vector C00, C01, C10, C11. And the outcome will be a vector Z00 prime, C01 prime, C10 prime, and C11 prime. And then we can, as always in quantum gates, also this matrix is a unitary matrix, and that is the matrix, the unitary matrix U C0 that describes the C0 operation. And here, this, of course, as we defined last week, last lecture, is the state vector psi for 2-qubit state, and that here is then in our notation the psi prime. So this whole thing basically means that there is a change in the target qubit based on the state of the control qubit. Turns actually out, so this is sort of the theory of the C0 gate, and it basically connects the states of 2 qubits in a very interesting way. We are here, at least for now, not discussing how such a gate is really implemented in practice. The scheme how to achieve that can be actually quite complex. So for example, for trapped ion quantum computing, there was a famous scheme developed by Ignacio Cirac and Peter Zoller in the mid-90s, 1995, for trapped ions. And that really, really kicked off the wave of trapped ion quantum computing, because basically was the first time that for trapped ions there was a concept developed that would actually implement in a practical system this C0 gate. Okay, now with this knowledge now of single qubit gates and 2-qubit gates, we can start to build non-trivial quantum circuits. And we are considering 2 examples here. And the first one is already a very useful and important one. We have here 2 qubits, and we send the first one first through a Hadamard gate, and then we apply a C0 gate where the first qubit is our control qubit, and the second one is the target. And well, we try to figure out what is the outcome here of this circuit. And let's go through it step by step. So we do step 1, which is we apply the Hadamard gate on our first qubit, which is in state 0. And as we said before, Hadamard gate is very important because it turns a 0 state into a superposition state. And the outcome will be a superposition, equal superposition of the 0 and the 1 state with prefactors 1/√2 to keep the normalization. So that means now with this Hadamard gate applied, we have for the total quantum state of the system, psi, we have the product state that is comprised of the superposition state that we just created with the Hadamard gate for the first qubit, and state 0 for the second qubit. And we can write that out as 1 over square root 2, 0, 0 plus 1, 0. Okay. And now let's apply our CNOT gate. That is the next step in the circuit. So we try to figure out what our output state psi prime is going to be. And we just do it by applying our matrix that we just defined a few minutes ago on our state psi. Well, how do we write that out? Well, the state psi, since it's a two-qubit state, we write it out as a vector with 4 entries, 1 over square root 2, 1, 0, 1, 0. So that is here, that is the vector formulation of this state. And then when we apply the matrix, the outcome of this is 1 over square root 2, 1, 0, 0, 1. Okay, and if we write this now out in bracket or in ket notation, our state psi prime is 1 over square root 2, 0, 0 plus 1, 1. And this state looks very innocent, but it's not. It is 1 of the so-called belt states. And these belt states are very important because they form a basis in the vector space or in the Hilbert space for 2 qubits. And second, they are maximally entangled states. So I write all of them out. And they all look very similar to each other. The first one is the one that we just created with a combination of Hadamard gate and the CNOT gate. So it's the 1 over square root 2, 0, 0 plus 1, 1 state. The second one is 1 over square root 2, 0, 0 minus 1, 1 state. And the next one is 1 over square root 2, 1, 0 plus 0, 1. And the fourth one is 1 over square root 2, 0, 1 minus 1, 0. Okay, and these states form the Bell basis for 2 qubit states. And they are maximally entangled. And this will play a role in the second part of the lecture. Okay. And the second example that we want to cover here is the so-called swap gate. Yeah. So the swap gate, as you can imagine, is supposed to swap the quantum states between 2 qubits. And the circuit for that can be represented by CNOT gates. but there is also a specific symbol just for this gate that looks like that. Okay, and of course the idea here is just to make sure this is not confusing. When you write such a circuit down, you always read it from left to right. Okay, let's then see how this sequence of 3 C0 gates actually acts on a quantum state. So let's have our input state AB, again, where A and B are element of either 0 and 1. And the first C0 gate is going to make out of it A plus B modulo 2. The second C0 gate is making out of this A plus modulo 2, A plus modulo 2 B, A plus B modulo 2. And this you can simplify to B, A plus B modulo 2. And then the action of the last C0 gate is going to turn this into B, A plus B modulo 2 plus B modulo 2. And that you will find, when you think about it, will simplify to B, A. So as one would guess, this circuit swaps the state or swaps 2 qubits. Okay, so these are 2 very important examples for 2-qubit gates, or for quantum circuits that involve 2 qubits. And really, the entirety of quantum information processing is about building up more complex circuits using these building blocks to make meaningful calculations. And at the end of the calculation, we always make a measurement on the quantum state, as I already showed you before in our diagram of what happens when we have a quantum logic circuit applied to a n-qubit register. And so I just want to make sure I discuss every element in completeness. And a measurement, as you know, converts a qubit state psi C0 0 plus C1 1 into a probabilistic classical bit which we can give the label M for measured bit, which is 0 with probability absolute value squared of C0, and it's 1 with probability C1 absolute value squared. And in quantum circuits, there is also a symbol for making a measurement, and that symbol is very visual. It is showing a meter. And then after a qubit passes through a meter, we write double lines. The double lines indicate that we turned from a qubit into a classical bit. So this is a meter symbol. And the double line in a quantum circuit always stays for stands for a classical bit. Okay, I see. That is basically all I want to say about this. Are there any questions? Yeah.
I just had a question about notation. I
Mhm.
remember last class we specified, when we have entangled states that, for instance, 0, 0, the right index was for qubit 1 and the left index was for qubit 2. But it seems here that you flipped that convention, so I just want to make sure I have it straight.
Did I do that? Maybe I did. Yes, you're completely right. Yeah, because okay, I see. Yeah, because here I changed that convention. Yeah. Thanks for pointing it out. I can't correct it now. So basically, it means we need to be careful to whatever the convention is. I'm not exactly sure how for the QuizKit part the convention is gonna be. Aiden or anyone else. Do we know that from the top of our head right now? Aiden?
Joseph, it would probably be better if you answer.
Is Joseph on? I don't know.
Yeah, this is in regards to the 0 and the 1 qubit.
Yeah. What is the convention for QuizKit for the entries in the kit?
So Henry uploaded a document on this. I think in the QuizKit notebook, the way they write it is the same way that you did, where 0 is 1 in the upper entry of the column and 0, like the 0 ket has 1 in the first entry and 0 in the second. But I think when you print it out in QuizKit, sometimes it might be backwards. So I would refer, I guess, students toward Henry's document since it can get very confusing.
Okay, we haven't distributed Henry's document yet, right?
It's uploaded on Courseworks.
Oh, it's uploaded already. Okay, good. So that's the important reference. So for what follows when we work with the IBM QuizKit system, we have uploaded a document where the notation is defined, and we'll follow that notation. So apologies for the slight confusion here, but it's just, we try to straighten it out, but be aware that any book you use, it may have different notation. So yeah, this was not intentional.
As a follow-up, this distinction in the convention sort of plays a key role in one of the problems on the problem set. Which way should we take it when solving that question?
Good point. If you define before what you do, either way is fine. You don't need to worry. So if you just say what your convention is, you can just follow that. If you point us to a specific problem, maybe we can send out a clarification if necessary. So maybe you can send a note to Aiden, and then if necessary, you can clarify it for everyone. Okay, sounds good. Great. And with that, I'll hand it over to Aiden, where my question is actually, should we do the break now, or should we first get started and do the break at exactly the time for the break? Maybe we first get started, right, Aiden?
Yeah, we can get started first. We can take a 5-minute break later. Yes. Could you hand me the host?
I do. Give me a sec here. Need to stop the sharing, and I need to make your host. Wait a sec. How can I make you host?
Let me just try to share my screen, and if everyone can see it, I think it's
probably good enough. Yeah.
All right.
Okay, seems to work. Very good.
All right.
Okay.
See me?
Then hand it over to you.
All right. Yeah. Thank you. Okay, hello everyone. So we're going to take a slight detour from talking about gates and quantum circuits, and we'll be talking about quantum entanglement specifically as a phenomenon. And we'll actually be doing experiments in the next 45 minutes as kind of a detour to actually demonstrate to you that quantum entanglement is something that is real and is uniquely quantum and doesn't have any actual classical analog. Right. So the learning objectives for this section will be fourfold. The first is that we want to demonstrate, like physically, like how we can actually achieve quantum entanglement. We want to understand what the so-called Bell inequality, which the experiment revolves around. We want to actually obtain a measurement of a violation of this inequality, and we want to show that of how this result of this violation actually proves the non-locality of quantum mechanics, and we'll be explaining what non-locality means as well. So this whole debate about locality in quantum mechanics actually started like back in the early 20th century with these three folks. So Albert Einstein, Nathan Rosen, and Boris Podolsky. And they were actually, so you need to remember that during that time was when quantum mechanics was first being studied. So there wasn't like, so it's not as well established as what we actually know today. And they were actually like really uncomfortable with the notion of quantum entanglement and measurement. And they were so uncomfortable that they actually wrote a paper about it. And over here, I'll summarize like the main points. Like this is actually extracted from the abstract of the paper. So the first point was that they believe that the description of reality cannot be given by the wave function in quantum mechanics, or that it is not incomplete, and that these two quantities, so the description of reality and the wave function in quantum mechanics, are incompatible basically. And it does lead them to conclude that the description of reality as given by a wave function is not complete. And specifically, they're referring to the example of measuring Bell states when they refer to this term of the basis of measurement being made on another system that had previously interacted with it. So to summarize what the main points are of their discomfort, which we'll refer to as the EPR paradox, named after them, was that they were very uncomfortable with the notion of a wave function, where the idea of a measurement disturbs the wave function, because they demanded that the physical variables associated with the measurement has to be measured with certainty, just like in classical mechanics. So they were not satisfied with the statistical interpretation of the wave function, and that we commonly accept as the Copenhagen interpretation, which we see over here. So you can imagine, like for example, like the wave function has like some sort of like finite spread in position space, for example, in x and y over here. And then it's only after you measure it does it collapse to one of its many probabilities, which is represented by this like small little delta function that we understand as a so-called wave function collapse over here. And so they argue that there has to be a deeper meaning associated that is not explained by it. So yeah, so just to recap what a 2-qubit, or for example a product state being, where suppose we have like two particles, 1 and 2, where each particle can occupy its own two-level system, which we refer to as the 0 state and the 1 state over here. And let's say that like we have like in state 1, it's formed by 1 over square root 2 of the 0 state plus the 1 state, and for particle 2 is basically prepared in the 1 state. And just as a reminder, how just as a reminder, if you wanted to actually prepare your particle 1 in this state, if it was originally in the 0 state, you would apply what gate to it? So I'm going to
H.
particle 1. Yeah, exactly. You apply the Hadamard gate to it. Exactly. And for the particle 2, what gate would you use to actually apply to it? It would be the X gate, right? In order to change the states.
Exactly. Yeah, there's an X gate in the answers. Great.
Yeah.
Or a pi pulse.
Yeah, exactly. Yeah. So yeah, all pi pulse, exactly. So in this situation, then you will want to write, you can write the tensor product of these two states, just explicitly writing it out as the 0 state tensor product with the 1, and similarly the 1 tensor product with the other one. And you can write out your combined two particle wave function as such. Okay. Yeah. So the full 2 particle basis can be represented in the following set, where it's given by the 0, 0 state, the 0, 1 state, the 1, 0 state, and the 1, 1 state. And if you wanted to write it like more generally, we can write it as in the following form, where each of these states has an associated like coefficient attached to it, like C00, C01, C10, and C11 for each of the for each of the related state respectively. And you can make any general product state out of all of these contributions. And we want to emphasize that entangled states just occur naturally out of the full Hilbert space as one of the many possible combinations. So it's not something that like it's spooky or like or weird. It just comes out naturally. And yeah, and there's a quote by Sebastian over here where he says, like quantum mechanics allows us to stitch together interesting wave functions, but it just so happens that some of them happen to be entangled. So a little bit more detail about entangled states. You can always write any combination of single particle states as a multi-particle product state. But the reverse is not true. And there exists multi-particle states that cannot be expressed in terms of a product of single particle states. And then you might recall, this is one of the possible forms of a Bell state. And when you are unable to do that, that means you cannot write it as a combination of single particle states, then this state is said to be entangled. All right?
That actually attaches also to one of the questions that came in the last class. I think the question was related to the combination of single particle states. Can be written as multi-particle product state, but the reverse is not true. So that's basically the answer to one of the questions in the last class.
All right. So what we mean by that is that the particle wave functions cannot be separated. And when you actually make a measurement on one particle, it actually affects the state of the other. For example, like the immediate collapse of the other wave function, even though you are not directly measuring it. And this was a big issue for EPR because to them it appeared that there seemed to be an instantaneous information transfer. So if you wanted to look at the paradox in more detail, let's assume that we prepare our state in this Bell state, the 0, 0 plus the 1, 1 state. So let's imagine a situation where we generated this like a entangled photon pair. And then like two individuals, Alice and Bob, they each took one of the photons and they moved billions of light years apart. And in our toy model, let's assume that Alice measures the state of her photon 1 and instantly collapses the state of Bob's photon 2. If I were to ask you how do we actually resolve this paradox, how what would be the reason why? I'll just give you a couple of moments to think about it. Yeah, so in conclusion, like this actually does not like violate any form of information transfer. For example, like information cannot travel faster than the speed of light, because the measured state that Alice gets and that Bob gets is still completely random. It's still like a 50% probability that you measure it in state 0, and a 50% probability that you measure in state 1. So just by using entangled photons by themselves, they cannot actually be used to transmit useful information. And if you were actually just to look at the states that Alice and Bob measures, like you get completely random states individually, but what you do get is that you get perfect correlation between the photon states that you measure. So for example, like if you know what state Alice gets, you definitely know what state Bob gets, but you don't, and that's what is unique about entanglement.
So basically here in that table you show for separate measurements like 1, 2, 3, 4, 5, you get different results in each row, but row Alice and row Bob is perfectly correlated, right?
Exactly. So we're going to take a brief moment to talk about measuring in, for example, like a rotated basis. And what you see here, for example, if like this is not the block sphere. I just want to make this extremely clear. But this you can imagine it as, for example, like a two-dimensional like a Hilbert space, where along the horizontal axis is the state 0 and the vertical axis is the state 1. And let's say like we wanted to measure what our state would be in like when it's rotated to, for example, like a state minus and state plus over here, where we can where they're related to state 1 and state 0 given by this matrix, which if you might notice is just equivalent to like any arbitrary rotation in a 2D plane, the cosine minus sine, sine and cosine over here. So this measurement in a rotated basis will be extremely useful for the experiment that we will be doing. So as mentioned, we assume that we prepare our two photon states in our 0, 0 and 1, 1. And over here, alpha is the angle that we are going to measure or the angle of the rotation of our basis given by here. Beta is a secondary angle that we'll be using later as well. Yeah. So just to drop the notation for convenience of the alphas. So if we actually measure in a rotated basis by using the same basis, we actually find that we still get perfect correlation. For example, if we measure one of the photons in the plus state, the other photon will also be measured in the plus state. And similarly, in the minus and the minus. So if you rotate the basis once for both of the photons that you're measuring, you still get perfect correlation. Now, what happens if you actually measure the photon states at different angles in the rotated basis? And let's say we measure the first photon when it's rotated by angle alpha. And if we measure the second photon when in the basis that is rotated by a different angle, beta. And this entirely ties into an experiment where we measure this so-called Bell's inequality, or better known the CH-SH inequality, as applied to entangled photons. So
yeah. So actually, before you continue, sorry, I just wanted to really emphasize again. It's quite amazing when you rotate the basis, entangled state stays an entangled state. So you can rotate the basis, but the entanglement completely survives. Mm-hmm. In an entangled state that's expressed by a wave function, like shown here. So that's just to really let that sink in. And I think there's a p-set problem for that, right?
Yeah.
Yeah. Good. And actually, just looking at the clock, is that a good point to make the break?
I can, if it's fine, I can take like 5 more minutes to just show the results, and then we can.
Sounds good. Yeah. Very good. Yeah.
Yeah, so this experiment can actually be done. Is actually going to be done in Pupin in like a minute or two. And this is an actual like full setup, which is created by the company QuTools. And yeah, and we're actually going into more detail about how it works. So just very briefly, what's happening here is that we have our entangled photon pair as prepared in, for example, like this state, 0, 0, and 1, 1, and we're going to send it into two separate photodetectors, so this that we can distinguish. And each of these photodetectors will be set, for example, or they have a polarizer in the path, and they're going to be set at different angles. So alpha for photon 1 and beta for photon 2. So the polarizer only allows light when the light of the polarization when it's aligned with the angle of the polarizer, and that's how we can distinguish the different states. And we can write the probability of, for example, like measuring the plus state when the basis, the plus minus state when the bases are rotated to an angle alpha and beta of our initial entangled state, and we write it. Sorry, yeah. So this is a small mistake. This should be plus minus over here. Let me just quickly correct it, just so that there is no confusion. Yeah, and just as a reminder, our basis rotation follows this rotation matrix seen over here. So I need to explain two more variables to you. The first is the expectation value. So it's the measurement of the correlation minus the anti-correlation. And over here is just a probability that the two photons are correlated in the plus and minus, and minus the probability that they are anti-correlated. So for example, you measure minus plus and a plus minus.
Just to add here, where the first plus refers to the plus state of the basis that's defined by rotation angle alpha, and where the second plus refers to the plus basis state for the basis that's defined by rotation angle beta.
Exactly. Yep. And then we need to define a second variable, which is what we refer to as a correlation function of different basis angles. So over here, we have two alpha, which we have two alpha values, alpha and alpha prime, and two beta values, beta and beta prime. And then we'll be measuring the expectation value at different combinations of the alpha and beta angles given by this equation. So there are locality arguments made by EPR restricts the value of S that we measure to be between -2 and 2. And if we get a measurement where S is greater than 2, that means it disproves any local theory, which means that quantum mechanics is non-local. Okay, so sorry. So over here we'll take a brief detour. So what we have here, I think the lights turn off in this case. Oh yeah, so over here, what you see here, oh sorry, I guess it's not showing it.
Yeah, right.
Let me pause and share Google Chrome. Yeah, so over here, what you see is me like a remotely accessing the computer that is set up next to our QuTools experiment. And what you see here is our entangled photon source, which is given by this white box. There's a little hole where the entangled photons come out. And then it bounces between these two mirrors and enters our photodetector, if you wanted to, as a simple explanation. And our two polarizers are these two things over here that can be remotely controlled where the angles can be remotely turned over here. So now I'm going to run an experiment where we're going to run through a series of angles, and hopefully we see a measurement of S that is greater than 2.
Maybe you can describe what's happening right now on the screen?
Yeah, absolutely. So what you see over here is that it's rotating the angles of the alpha and betas to set to certain values over here, and similarly over here. And yeah, and so then it's getting the photon counts in order to calculate the probabilities of which they then use to calculate the expectation values of your different alphas and betas, which they then use to calculate our S value here. And yeah, and so over here we see that we have just gotten an experimental measurement where we found S to be 2.28, which I hope and with an error of 0.026. So this is at least like 10 standard deviations from the two. And if you recall, like from that the typical standard deviation that we need for that the community usually expects for proof is about 5. So I hope that this demonstrates to you beyond reasonable doubt that quantum mechanics is non-local in this scenario.
Can you maybe like widen the tab you have here? It's quite hard to see what's on this. Yeah.
Right. Is that better?
Much better.
Thank you.
Yes.
Yeah.
Yeah.
Right.
Thanks for the note. Yeah.
Yeah. Thanks for letting us know. Yeah. So this is the S value that we just measured. I think.
And then the numbers, just to also point that out, the numbers here above, these are actually the rotation angles of the polarizers, right?
Yes, in degrees, absolutely. And the blue value here is just the photon counts, for example, that we'll explain later, how this number is actually calculated. Yeah. All right. So I think it's a good time to take a 5-minute break at this moment.
Maybe say 3 minutes and we continue at 3:45.
Yeah, sure. 3 minutes is fine.
Sounds good.
If you have any questions, I'll be happy to answer them now as well.
Thank you.
Ja, das weiß keiner, was das sein wird. Weil wenn es jemand wüsste.
All right, I'll give like 30 more seconds. Just share screen.
Yep. Yeah, so that's actually it's the experiment that you just saw. That's in the 6th floor of Pupin Hall, and it's probably the first time since we have this setup here that Bell's inequalities were broken in New York City. So this is a new setup that we just got like a year ago. So it's and allows them to do much more than what you just saw. And it's if you're interested, there's like several project possibilities also on this setup. So Aiden has been the tutor for the lab over the last year and really developed like fantastic material and ways how to use this setup for interesting experiments. For example, interferometry with single photons and also quantum key distribution, which is an important concept in quantum communication. And you can you do quantum teleportation actually?
No, you need
that doesn't work, right?
That you need at least one more source.
Yeah, right. Yeah, okay. Yeah, okay, but that will come actually. That will actually arrive at some point. Not sure it will arrive in the next two weeks.
Yeah.
Anyhow, okay, yeah.
All right. So back to it. I hope everyone's back. So just to recap what we actually saw like about 3 minutes ago. So if you choose angles that you measure, like carefully, you can actually measure a value of S that is actually greater than 2, which implies in this case that locality, which they describe as classical hidden variables as well as proposed by EPR, is wrong. We will explain what this idea of hidden variables is like in a later slide. So right now we're going to dive into understanding what actually happens in the experiment. So the first step is actually generating an entanglement. So in this case, what actually happens is that we, in order to generate our photons, our basically 2 exactly identical photons, how the experiment does it is that they first start with a single pump photon that has a wavelength of about 470 nanometers. That's why it's referred to as blue over here. And what they do is that they shine it onto a nonlinear crystal. And via this process called spontaneous parametric down conversion, our initial photon of a certain energy h bar omega is going to be split into exactly 2 photons with identical energy. So h bar omega and h bar omega 1 and h bar omega 2, where omega 1 and omega 2 are equal. And due to the 2 conservation laws of energy and momentum, this enforces that our 2 photons are exactly identical. And are exactly identical. And that's only 2 photons being created in this process. And you can see, so for example, we can imagine that like if we initially start with 1 photon with, for example, a horizontal polarization, in this case, a pump photon, it generates 2 photons that have vertical polarization, like V1 and V2 in this scenario. But that is not sufficient to actually for sufficient entanglement. So how we actually achieve entanglement is by sandwiching 2 of these crystals together and sending in pump light that has both half vertical and half horizontal polarization. And how we actually do that is by doing a kind of like a pi over 2 pulse using an optics like element called a half-wave plate that's able to rotate the polarization of our initial pump photon into a 1 over square root 2 horizontal plus vertical over here. And when we send in this polarization into our sandwich nonlinear crystal, we then generate our entangled photon source over here. You might notice the similarities of the convention that we usually use.
So actually, just one comment here. So it shows you actually that, you know, we discussed some abstract gate operations before. But whenever you have a real physical system in which you want to realize these gate operations, always means something different. In the case of photons, a Hadamard gate means that you send a photon with a certain polarization, like horizontal here, through a half-wave plate. And then you get a superposition plate, a superposition state out of it. When you use an atom and you want to do that, you need to apply a radio frequency wave and make a pi over 2 pulse. You know, in a similar in a superconducting qubit. So you know, basically all qubit systems have also their own way of how you realize these different quantum gates.
Absolutely. And depending on your system, some ways are easier than others.
Right.
Yeah. So if you recall, like the little like white box that I was showing you, this is a picture of what it actually looks like inside. And over here, you can see the actual implementation of how we actually generate our entangled photons, where the blue light is our source, and this is our special sandwich nonlinear crystal over here that generates our entangled photons. So just to go back to part of the flaw interpretation, or rather like locality. So what we mean, or what EPR meant by that, is that locality means that when you measure photon 1, you cannot modify instantaneously the result of measuring photon 2, which ties into the idea that there is no action at a distance faster than light. So in order to resolve this paradox, the EPR's resolution was the introduction of a so-called classical hidden variable lambda that does, number one, respects the locality given by general relativity, which, you know, we can imagine where the idea came from, or rather who the idea came from. And number two, that it also reproduces the statistics of quantum mechanics. So for example, this lambda here can be something like a polarization angle that relates the two photons together that was created when these two photons were created, and it just travels along with them wherever they go. So what this experimental test of Bell's inequality is that it's actually just a quantitative measure of how much we can actually violate locality, where we are interested in the measurement of single photons at both photodetectors at the same time. So just as a reminder, you can assume that our two photon states are prepared in our 1 square root 2 horizontal plus vertical that we will now simply rewrite back in our 0, 0 and 1, 1 state, like for convention. So our horizontal state is we'll just write as a 0 state, and our vertical we write as a 1 state, where the same basis rotation applies. And then our probabilities, for example, the probability of measuring both states in the plus state basis. So recall that alpha refers to the angle that you set for the angle of the polarizer that you set for photon 1, and beta refers to the angle of the polarizer that you set for the second photon. All right, and if you take the equations that they are given over here, and you calculate them out, what you get is that this probability that you measure both in the plus state of of the different angles is given by half of cosine squared multiplied by beta minus alpha. And if you do the same for the minus state, you get the exact same probability. And the inverse, sorry, or not the inverse, but the probability of measuring in the plus state for your first photon and the minus state for your second photon when at the different angles is half times sine squared of beta minus alpha. And and similarly, this is also the probability that you get for the minus plus states. And you will notice that all these probabilities, they only depend on the relative angle beta minus alpha. Yeah, and so for example, like if you were to imagine that if you set the polarizers to be at the same angle, or so-called parallel, in this case, where beta equals to alpha, then you get probability of plus minus is equal to the probability of minus plus, which is equal to 0. Yeah, so previously we defined what the expectation value of the correlation minus the anti-correlation, and your half cosine squared term is also or rather like your half cosine squared term, you apply to these four values, you get cosine 2 of alpha minus beta. So expectation value is also only dependent on the relative angle. And this expectation value spans all possible measurement outcomes, and you can find that E will hold value between -1 all the way until 1. You notice that when alpha and beta are 0, your E equals 1 in this scenario. So all your individual measurements will be random, but it's just that there will be correlation between the random results of your two photons. And the second variable that we defined was our S correlation function, which is as given by this, which is just as a reminder, it's the correlation function for different basis angles. And this S value is a function that can quantify locality into an experimentally measurable effect. So locality in this scenario actually restricts our expectation values, alpha and beta, through the hidden variable lambda to be real. And it has to hold a value of either 0, -1, or +1. And if you were to put in all these three possibilities, you would find that, that this is what actually restricts our S value to be between -2 and +2. So saying that, any measurement of our S being greater than 2 would then disprove any local theory, which then means that quantum mechanics can only if quantum mechanics is non-local, can the value of S be greater than 2. And if you were to substitute the following angles for S to -45 degrees, 0 degrees, 22.5 degrees, and 22.5 degrees, you actually find that the maximum violation that you can measure is a value of 2 multiplied by square root 2, which in this case, it would be something like 2.816 off the top of my head. All right. And yeah. So in the experiment, instead of measuring probabilities, what we actually do is that we actually measure the photon counts. So how we actually do that is by measuring the, for example, correlated photon counts minus the anti-correlated photon counts, and we divide that by the total 2 photon counts. So N over here refers to the 2 photon coincidence counts, where we measure at the same time both photons being in the plus state, minus state, and similarly for all the other variables. And this is instead how we actually calculate the expectation value. And for S, we calculate it by the same way for our different basis angles. Yeah, or rather, we calculate S the same way, like for expectation value at different basis angles. Yeah, and just to quickly summarize, we want to reemphasize that quantum entanglement is a real and demonstrable and real effect, and has demonstrable effects on experimental measurements, and that S, this correlation function, is a quantifiable measure of locality, and that if you do measure a value of where S is greater than 2, this implies that classical hidden variables as proposed by EPR is wrong, which means that if there are no hidden variables, that means locality is not possible. And it means that quantum mechanics must hence be non-local. And as a fourth point, we also want to emphasize that entanglement by itself cannot be used to transfer useful information faster than the speed of light. Yeah, and this is a measurement done at another time where S was found to have a greater violation than the 2.2 that we measured. Yeah, and also just to getting started regarding the projects that you're interested in doing. So written over here is a link to the company webpage. I actually made made the setup where they have a list of a ton of interesting experiments that you can do like for your project. There's two that I've done extensively with with other students as well, if you're interested, and they are the Hong-Mondor interference, where you see this effect of a boson bunching. So for example, if you send in 2 bosons into a beam splitter, you find that they always leave together, and this is purely quantum statistical phenomenon. And the second is the single photon interference, where if you send in a single photon through a path, where classically, if you were to be doing it, that's a similar analog of the Michelson interferometer, where you send light through a beam path, then it will interfere. You'll find interference. But what happens if you actually bring it all the way down into the quantum realm, where instead you send a single photon that, if we were to imagine as being purely an indivisible particle. And what you see here is that even with single photons, you can also measure interference, where these fringes over here are your interference patterns of your photons. There are also many other possible experiments that you can look at the website and see if you can see if you're interested in doing this. Of course, it will definitely be much easier if you were on campus. But if you're still interested in your remote, then let me know, and we can probably discuss additional options. Yes, that's it from me.
Great.
Are there any questions about anything?
Yeah, we have still quite some more time, actually. Right, yeah, we have more time. So, anything you're interested in, you can go back to also.
Yeah.
Maybe you are wondering really how locality is really, constraining the E function to values 0, -1, and +1. Is that a question that people have? Maybe Aiden can comment. Just in case it was a question that you have.
It's a lot more involved. At least the mathematics, the math behind it is a lot more involved than.
Right. So basically, you assume for that you don't have a probabilistic wave function, but that you have a wave function where basically there is a variable, a so-called hidden variable, that predetermines the outcome of the measurement. And any theory that you write down that has such a hidden variable that predetermines in a deterministic way the outcome of the measurement, it's bound to lead to this E correlation function to be either 0, +1, or -1. And with that, it bounds the function S that is introduced here, which is a combination of these four different E functions measured for 4 different angles. It bounds it to between -2 and 2. But in the experiment, we demonstrate that it's possible to measure S values that are larger than 2 or smaller than -2. And that excludes them really, the local theory hypothesis. And it's, it's actually even worthwhile as a project to really work through that and really think that through. It's also a possible project to really, for yourself, try to clarify all these elements. And it is actually, it's a cutting edge point of research until today. So the first Bell test that was done 35, 40 years ago. I'm not exactly sure about the exact year, early 80s, by Alain Aspect, using exactly entangled photons as in the setup that you just saw. In the old days, that was, of course, a lot more complicated to do because all this electronics to measure coincidence counts and all that stuff wasn't available. So it was much harder, but it was shown back then. And, and since then, Bell tests have continued because you may even think, well, if the detectors for the 2 photons are sitting too close to each other, there may be some way how at the speed of light there can be some sort of some sort of communication between these detectors, which then determine the measurement outcome. So there has been, it's a real cutting edge research topic to figure out so-called loophole-free Bell tests, where you make sure that the detectors are separated such that they cannot be detected, in a relevant way by communication that happens at the speed of light. So just, every year there are new variations of this experiment that are coming out that close more and more loopholes and prove that the probabilistic interpretation of quantum mechanics is actually real. And that really connects then also back to, basically the slideshow from a week ago, where I said, like, there are basically 3 main things that determine, the potential of quantum mechanics to lead to new technology. And number 1 was discrete energies. Number 2 was superposition states, where we now saw, well, in the quantum gate interpretation, you create these superposition states with a Hadamard gate, or with photons, you use a half-wave plate. And then the other thing that is crucial is entangled states. And we just saw today that you create entangled states by combining Hadamard gate and a CNOT gate, for example. And in the photon case, we create entangled states by using this process that Aidan described, that's called parametric down conversion. So we have now all these 3 aspects now, covered, and a large part of the class that follows is trying to learn how these kind of 3 aspects can be used to put together interesting quantum algorithms. How did we arrive? There's a question, maybe Aidan, for you. How did we arrive at the entanglement conclusion on the penultimate slide? That entanglement cannot transfer information faster than C.
So it ties back to the idea of entanglement just by itself. You cannot actually transmit information, right? Because, for example, like you cannot, if you took if you generated 2 entangled photons, right? And then you, like Alice and Bob in the toy example, and then you took it millions of years apart away from each other. Like, there is no physical way that you can send information using your photon, if you're Alice, to Bob. Because all you're going to do is that it's just going to, the information by itself is just going to be entirely random. So it's going to be random, and you can actually send information like from one point to another. So there will be a scenario, or there is like this phenomenon called quantum teleportation that you'll be learning later, where it utilizes entanglement to basically transmit information from between two people, but that involves a transfer, but that involves an additional unit of information where you have to basically report your measurements like through so-called classical channels, which then is or like via, for example, like a bit, which then is restricted to traveling like not to transmitting information below the speed of light.
At or below, yeah.
At or below the speed of light. And we will definitely go into that actually in the next lecture.
So it all boils down really to the randomness of the measurement. You have an entangled state, 0, 0, 1, 1 plus 1, 1 maybe. But you know, if one party measures their qubit, or if one qubit is measured, it is correlated with the outcome of the second qubit, but still the initial measurement gives a random result, and therefore no information. There is an instantaneous action between the qubits, but since the measurement itself is random, the result is random, you can't really use it directly to transmit information. Okay, there's another question.
Yeah, I just saw like one question. So like for today at the beginning of class, we talked about where like we basically have like a quantum like registry where we have these like all these like different number of qubits. And I was just like curious, like, and what are the current ways where people prepare the qubits? I know I've read some different parts about different techniques, but is there like what are the methods out there in the current research? Like, can you maybe give like a rundown or like a little?
Yeah. So that, yes, I'm happy to give you a rundown, and there will be later in class in the seminar part, we will have basically speakers from different communities that explore different hardware systems, which then really is an opportunity also to really dig a bit deeper. But basically the thing is that the hardware question is a cutting edge research question right now still. Where different systems are explored. Systems that have quite matured and are quite well engineered today are especially superconducting qubits, and that I mentioned in our last week, I think, and trapped ions. That has very much to do with when these research fields were started. The first lab experiments for superconducting qubits were done in the 90s. And Josephson junctions were already known for much longer than that. And for trapped ions, the first lab experiments were in the 80s. But there are a number of other platforms that are catching up rapidly and which basically are lagging behind in the engineering, but the basic physics is indicating that they are also extremely promising. Among these platforms is neutral atoms, where you use basically the orbitals of atoms as qubit states. They are promising these days because you can cool them down to ultra cold temperatures, which means you can basically bring single atoms to a standstill and trap a single atom, and then you trap another single atom and another single atom and another single atom. And out of this chain of single atoms, you can basically build up a quantum register. So that has been rapidly developing over the last 3 to 5 years, and we are also setting up experiment actually right here at Columbia on this. Another system that is interesting is called nitrogen vacancy centers. It's basically you take a piece of diamond, and there may be defects in the diamond that are made out of nitrogen atoms. And it turns out that these defects act very much like artificial atoms in themselves. And if you organize things in the right way, you can actually realize quantum gates with those. And single qubit quantum gates definitely work. It's very much related to NMR, nuclear magnetic resonance, and even 2 qubit gates are demonstrated. So these are two of the more promising upcoming platforms. There's also ultra-cold dipolar molecules, which is even more new, and we are actually also working on that in our labs and see how far we can drive it. But there's a whole range of other hardware platforms out there. But it gives you what I said, gives you basically a rundown of maybe the most the hottest ones in the current race. But it's an interesting situation because basically the theoretical concepts are there, but the experimental hardware is still an undecided question. So it's a very exciting time for this kind of research. And as I said, there will be more opportunities to discuss that in details in the course of the class. And it can be also a part of a project. You can come up with your own project ideas that you can define, and investigating and reviewing certain qubit types can be also with an eye on the experimental realization, can be also a possible project. Okay, I think we are, in terms of time, we reached the 4:15, and Edita shared a paper also. I didn't open it yet. Yeah, this is a very nice paper
it's the PRX.
about yeah.
Sorry, yeah, it's
Edita,
the PRX paper where they just quickly overview, well, not quickly, but they overview all the different architectures that currently exist, and they also look at the advantages and disadvantages of using one versus the other. So I thought it was really cool to read, because I also had a lot of questions on how many different things are and which I don't know which direction I should go into. So it's a good paper.
Mm-hmm. Yeah, I agree. This is a very good paper. Great. Yeah, so let's conclude it for today and see you next week. Thanks so much, Aiden, and yeah, see you all soon. Bye-bye.
Goodbye.
And tomorrow,
Thank you.
tutorials, of course. Yeah, tutorials. Yeah. Good.